we're going to review NSA2, number systems. This standard tells us to use rational approximations of irrational numbers to, among other things, compare the size of irrational numbers. Now, I think it's important that first we review irrational numbers. Irrational numbers are numbers that cannot be expressed in the form a over b, where a and b are integers, and we know that their decimal expansions do not terminate or repeat. Let's look at some examples. For example, 7.325973684015, on and on and on, does not end or repeat. Therefore, it is irrational. Pi does not end or repeat. It's also irrational. The square root of 2 is equal to 1.414214,562, and that goes on and on and on. It does not repeat. Just so you will know, the square roots of all non-perfect squares are irrational numbers. What are non-perfect squares? That would be things like the square root of 2, the square root of 3, the square root of 5, square root of 6, things that are not perfect squares. Another part of that standard is that you're supposed to use rational approximations of irrational numbers to locate irrational numbers approximately on a number line. Here's an example. What if we were trying to find the approximate location of the square root of 2 on a number line? We start out by drawing the number line. And as you can see, you've got your number line drawn right here. Then we want to add the locations for perfect squares. With our number line, we've got 0, 1, 2, 3, and 4. We know that the square root of 1 is 1. That goes right there. We know that the square root of 4 is 2. So that goes right there. We know that the square root of 9 is 3. So square root of 9 goes right there with 3. And we know that on a number line, the square root of 16 is 4. So that goes right there. Now, what if we want to add the locations for the non-perfect squares, or for the square roots of some non-perfect squares, such as the square root of 2, the square root of 3, the square root of 5, the square root of 6, square root of 7, square root of 8, square root of 10, numbers like that? Where would they go? Well, let's look at our number line down here. If we're looking at our number line, we see that between 0 and 1, none of these would go there because the square root of 1 is equal to 1. The square root of 4 is equal to 2, so that square root of 2 and square root of 3 would have to go between 1 and 2. See, square root of 1, square root of 2, square root of 3, square root of 4. Okay? How about the square root of 5? Well, if the square root of 4 is 2 and the square root of 9 is 3, all these other numbers between 4 and 9 have to fit in here. Square root of 5, square root of 6, square root of 7, square root of 8. Oh, and then the square root of 9 is 3, so we're back to here. And we know that if the square root of 16 is 4, then the square root of 9, square root of 10, the square root of 10, square root of 11, square root of 12, square root of 13, square root of 14, square root of 15 would have to fit between 3 and 4. Notice that the square root of 2 is between 1 and 2, and we're looking for the square root of 2. That's what we're looking for. It's between 1 and 2. But do you see how it's got both the square root of 2 and the square root of 3 in here? That would tell us that basically 1.5 should be right here between the square root of 2 and square root of 3. So the square root of 2 is going to be somewhere between 1 and 1.5. The square root of all non-perfect squares are irrational numbers. Square root of 2 is an irrational number. Now, we've got one more toward the bottom here we want to look at. Which would have a greater value, 4 or the square root of 7? Let's look up here at our number line. The number 4 is equal to the square root of 16. Now, when we were looking at it down here, we said the square root of 7 was here between 2 and 3. If square root of 7 is between 2 and 3, it's got to be less than 4. You can write an inequality looking at this. The square root of 7 is less than 4. And then there's one more part to the standard that we want to look at. You can use rational approximations of irrational numbers to estimate the values of expressions. Here we're saying estimate the value of the square root of 14 to the nearest tenth. Let's see what we can do with that. We know if we put this on the number line, like we did earlier, put our numbers here and put our square roots for them here. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is equal to 2. Square root of 9 is equal to 3. The square root of 16 is equal to 4. The square root of 14 is going to fall between the square root of 9 and the square root of 16. So the square root of 14 falls between 3 and 4. Let's figure out how far it falls between the two. We can basically find a fraction here. We know it is 3 point something. Let's find what fraction it is by finding the distance between the square root of 9 and the square root of 14 over the whole distance between these two perfect squares. From 9 to 14 is 5. 14 minus 9 is 5. The whole distance of this range between these two perfect squares would be 16 minus 9, which is 7. We're talking about 3 and 5/7, 5 over 7. Okay? So now let's find the approximate value on 5/7. If I wanted to do this as a decimal, all I've got to do is divide 5 by 7. 7's on the bottom. It's left out of the house. It goes on the outside. How many times will 7 go into 5? It won't. We put a decimal here, put a 0 behind our 5. 7 will go into 50 7 times. 7 times 7 is 49. That leaves me 1. If I do it again to see whether or not I need to round this up or down, I've got 1. I bring down my 0. 7 will go into 10 one time. That's 7. So I've got 0.71. I would round this, leave this 7 where it is. 4 or less, let it rest. 5 or more, raise the score. So 1 is less than 5. It's 4 or less, so we let 7 stay as it is. The square root of 14 then is about 3.7 because 0.7 is approximately equal to 5 divided by 7, this fraction.